Okay, hello everyone. Can you please confirm if you can see the slides? Please send me a message in the chat box.
Yes, I can see him. And I
Oh,
hear you.
okay. Thank you. Thank you. Okay. So last time we just had a discussion, actually not discussion. I just explained what are the logistics about the course, like uh, what topics we are going to cover, what will be the grading policy, and so on and so forth. But we didn't have any, the real start of the course. So today we are going to have our first lecture. Uh, and in today's lecture, we are basically going to have, actually not only today, but also on Thursday. So we are going to have a grand tour of the major operating components of the operating system. And we will also have a coverage of basic computer system uh, features. So today we will basically talk about what operating systems do and what is the computer system organization, right? Uh, the today's lecture is supposed to address the course learning outcomes 1 and 2. So which and not definitely not completely, but only partially. Even when I say partially, it is like a, just some gist of those learning objectives, which is like understand the control and management of hardware resources, and also understand and apply management and execution of processes. But remember that the topics which basically address these learning outcomes, they will appear in our upcoming lectures as well. Like down the line, we will have separate uh, lectures completely dedicated to process management and about uh, how to say other features of managing the memory or hardware resources and so on and so forth, right? But here we will have just some discussion about hardware resources. Okay, so what an operating system does. So to answer that question, let's try to dissect a typical computing system. So we can divide a computer system into four main components. The one at the lowest level is the hardware of the computer itself. So which is basically responsible for providing the computing resources. So this is the hardware which is made up of basically transistors at the lowest levels. And those transistors are at the end of the day responsible for all the processing, for storing the for storing the data, and for all the communication between CPU and memory, right? On the other end of the spectrum, or on the or let's not say spectrum, but on the other side, on the other extreme, we have users, and these users are responsible. Uh, Let me first check if the recording is in progress or not. Yeah, okay. So on the other side, we have users, and these are like users can be anything. These can be people or other machines, other computers, which actually want to use those hardware resources to do some computation, right? But users typically do not interact directly with the computer hardware. Uh, what they do is that they use the application programs to solve the problems, the computing problems for the user, right? So example of application programs like which everyone is familiar, common examples which are like everyone is familiar with them, or like for example word processors, compilers, web browser, database system, and video games, right? So even when users know nothing about the underlying hardware, they are still able to utilize that hardware by running their applications. But then applications, uh, as just like we know from this, like from our daily life experience, that multiple applications are running on the same hardware at the same time. So That's why that we have operating system which sits between computer hardware and the application programs, and it is responsible for controlling and coordinating the use of hardware among various applications and users which are using those applications, right? So this is like a very high level conceptual visualization of a typical computing system where we have four different components: users on the one side, computer hardware on the other side, and in between we have application program and operating systems. So if I ask that, then what is an operating system? Or I mean, how can we define an operating system? So operating system is a program which is responsible for managing the hardware, and it acts as an intermediary between users or applications and the hardware, right? So if we don't have operating system available, then it will be extremely difficult to manage the hardware, and it will be like a nightmare to manage multiple applications running on the same hardware. So if we just want to depict the same idea and graphically, so it will be like you have hardware on the one side and you have user applications on the other side, and then OS is responsible for managing those hardware resources and share them across multiple users and our applications. So what jobs an OS or what functionalities an OS operating system is supposed to perform? Uh, an OS is responsible for starting, terminating, and before terminating, definitely, while programs are executing, it is responsible for controlling the execution of user programs. Uh, and not only that, it makes the system convenient to use for an end user, like for uh, human beings or for people. If we are working on a computing system and we have an operating system available, it becomes much easier for us to use our machine as compared to the case. Just imagine where you don't have operating system and then you want to work on the hardware, then life will be much difficult for you. I I think all of you have taken the course of CSCI 2230. This is the new code. I guess the old code was 273, right? Assembly language and assembly programming and machine organization, right? So in that course, I think you guys studies a microcontroller. Right now I'm teaching that course. So just recall your memory that in that course you are dealing with a microcontroller, but you don't have any operating system there, right? So it is your job as a programmer to know all the internal details of the microcontroller, what type of registers it has, what is data address range, what is program code or code address range, what is IO address range, how you can interact with the IO devices, what special function register you need to program to interact with the outside world, right? So you need to know all the internal details, and then also you must program your device, that is microcontroller, in assembly language, right? Also, you cannot run multiple programs on that microcontroller at the same time. The microcontroller can do only one job at a time because it doesn't have an operating system. So it cannot support multiple programs running at the same time, right? And life is much difficult with the microcontroller. And one reason for that is that on that particular microcontroller, you don't have a operating system running on it, on top of it. So also, operating system is responsible for controlling and coordinating the use of hardware. It is responsible for performing and managing IO devices. For example, let's say in a system you have multiple applications running on the CPU, and uh, all of them or multiple of them are trying to access printer or your screen, a monitor or keyboard. So who will manage or who will coordinate the access to these IO devices for which multiple applications are competing at the same time, right? And not only that, the job of the operating system is not only to control and coordinate the use of hardware, but its job is also to do that in an efficient way. And when we say an efficient way, it's mean in a way where there is no wastage of the resources, and also the required job can be completed uh, in the minimal amount of time, right? In the lowest latency. Also, the job of the operating system is to implement common services, those services which are requested by multiple applications. For example, if multiple applications want to get input from the keyboard, so then it should provide this service of handling the input from keyboard for multiple applications. How? We will talk about it later, right? So in the previous slide, we have said that operating system is a code or a program which is responsible for coordinating and controlling the hardware and sharing the hardware resources among multiple applications. But that is just an understanding of how you define an operating system. There is no universally accepted definition for defining what an OS is or what an operating system is, right? So like one definition is like everything a vendor ships when you order an operating system is the operating system. So what does it mean? For example, let's say uh, if you have an Apple machine or let's say MacBook, so with your operating system you already have the web browser Safari, right? But is Safari universally considered, or any web browser is universally considered a part of the operating system? No, because there are operating systems which do not come with a browser application, right? So the definition can change from like one vendor to the other. However, there is a component of the operating system which is considered as the core component, and it is named as kernel, and it is the component which is running all the time, and it is responsible for providing most of the functionality of the operating system. Uh, when we say most of the functionality, it means that there are also some functional components which are not embedded in the kernel, but still they are part of the operating system. However, they are not considered as uh, as necessary components or other components without which you cannot build an operating system. So, other than kernel, everything else in the system is either a system program or an application program. So, system program is one which is responsible, which is basically associated with the operating system, and it provides some services, some kind of services to the application programs on behalf of the operating system. So, example of system programs in Linux environment are, for example, GCC compiler or Bash script, or GDB debugger or perf tool, right? So all of these tools, they come as a component of or as a part of the Linux operating system, but they do not constitute the kernel. These are system applications, and user applications then use these system program or system applications whenever they need them. For example, if you are running a user program or an application and you want to measure its performance in terms of different performance parameter, then you can use the perf tool,
Use it.
right? Okay. So similarly, debugger, for example, if you are writing a C program or any like C++ program and you want to debug it, then you can use this debugger tool, right? And it comes as a component. So it is a system application. Application programs are like which you can install on your own, or you can write the application programs on your own and then you can run them on top of the operating system. Okay. So uh, We remember we had a look at this picture in the previous lecture, and we said that a typical computer consists of like a CPU and memory device, and then a bunch of different kind of controllers, and all of them are connected with each other through a system bus, right? So here we have like one or more CPUs. Let's say initially we assume we have only one CPU, some device controllers, and a common bus and a shared memory. So common bus is responsible for connecting all these devices with each other. The issue here is that CPUs, definitely they are responsible for running the applications. And the device controllers, for example, in this figure, disk controller or USB controller, they are responsible. For example, disk controller is responsible for reading the data from disk, and then that data need to be moved to the memory, right? So if a CPU is running an application and a disk controller also want to copy the data from disk to the memory, then CPU and the disk controller, they will compete for the memory cycle, or basically they will compete to have access to the memory bus so that they can move their data to the memory. CPU is producing some data, and let's say it's want to write the result in the memory, and at the same time the disk controller is trying to copy the data from disk and put it in the memory. So they will compete for the memory bus. So in this situation, then the question is that how the memory is managed. Just like we have disk controller, for example, to manage the disk or any kind of read and write operation on disk. In the same way, we have memory controllers, which is not shown in this figure, and they are responsible for synchronizing the memory accesses or managing the accesses to memory by different requesters like first from CPU, disk controller, or any other kind of, for example, network adapter or any other kind of device which is allowed to make accesses to the memory. Okay, so let's try to answer some questions related to a typical computing platform. So if we have a computer system as shown in the figure, uh, let's ask the question that how such a system uh, is how what happens when such a system is rebooted, right? And also how then data is transferred between devices and memory. When we say devices, it's basically mean like how the data is transferred from disk controller to the memory, USB controller to the memory, from CPU to the memory, and so on and so forth, right? Like from graphics adapter to the memory. So also, as we will see during the discussion, the transfer of the data from any device or like any controller to the memory, it can happen in two different ways. It can happen with the intervention of CPU, or without, or let's say the loss intervention of CPU. So we will have a look at both type of approaches, like how we can transfer the data from a device to memory without intervention of CPU. And also we will talk about how the memory or storage is organized, right? So memory and storage, actually these refer to two different things. So memory is basically volatile memory, the memory chip which actually hosts the data, and storage typically refers to the devices which can hold our data in a permanent way, for example disks or tapes, right? Or SSDs, right? So we will talk about how memory or storage is organized. So let's first talk about the first question, which is like what happens when we reboot a computer. So at the time of reboot, we have a program which is named as bootstrap program, which is loaded at power up or reboot. And when we say loaded, basically it's mean that uh, we have this program available uh, all the time in read-only memory or EPROM, electrically programmable read-only memory. So it is like kind of firmware, right? So this program is sitting there in the chip, in the read-only memory chip all the time. And when we reboot a machine, this program starts executing, right? So this is the first program after restarting a machine that is executed. Uh, the job of this program or the bootstrap program is to initialize all aspects of the system. Basically, it means that it is responsible for loading the operating system kernel into the memory. Loading from where? Loading from your permanent storage, for example, from SSD or disk into the memory, and then start its execution. So once the kernel is loaded, then it's mean that operating system takes control of the execution, and then it is responsible for managing your all hardware devices and running all the applications which are launched by the users uh, on the machine. Okay. So here one question is like, as I said, that we store the bootstrap program in read-only memory or electrically erasable programmable read-only memory. The question is why we use ROM or EPROM to store the bootstrap program? Why we can't put it in the DRAM? Is there anyone who want to answer the question? If you want to answer, you can simply put it in the chat box, uh, or you can unmute yourself and you can talk. So the reason is that DRAM is, yes, it is also a memory, but it is volatile. Volatile mean that when you turn off your computer, the data in DRAM is lost, right? Actually, someone has cannot be volatile. Yeah, that's correct. So uh, so when you remove the power, the data in the DRAM is whatever you have in DRAM is lost, whether it is data or program, whatever it has. It is lost, right? So if you put our bootstrap program in DRAM, and when you reboot your machine, the bootstrap program from the DRAM will be is already gone, right? And then you cannot start your machine. So that's why you put it in read-only memory, and which is the read-only memory, and which is also non-volatile, right? Otherwise, you will not be able to reboot your machine. Okay. The kernel is the kernel is the component which is active and running all the time, and it makes the system ready for running applications. And kernel always reside in memory. What does it mean that it always resides in memory? Earlier we said that kernel is loaded into the memory. So now why we are saying that kernel always resides in the memory? When we say here that kernel always resides in memory, it means that as long as your machine is running, your kernel will never be kicked out of the memory into disk, because other applications, like you, if you have user applications, then and let's say there is a situation where you don't have enough memory, what will happen is that those user applications will be possibly kicked out from the memory and placed into the disk, and then they will be again loaded when there becomes space available in the memory. However, this is never done with the kernel, because kernel is responsible for managing resources and for running the application. So it always resides in the memory once it is loaded from the disk into the memory and your system is running, which means that power is available, right? Okay. So this was a very brief uh, uh, discussion of the question that what happens when we reboot a machine, right? And a machine which has operating system a capability to run the operating system, right? Now let's go to the next question, which was like how the data transfer happens between a disk controller or between a, let's say, between a device. And again, when we here I say device, it's mean all the IO devices, any type of IO device like disk, mouse, keyboard, printer, monitor, anything shown in the figure, right? So how the data transfer happens between a device and the memory. So before answering that question, we need to first clarify or first need to define some terms, right? So device controller is actually a hardware component within or attached to the device. So for example, as shown in this figure, let me select the pointer. So as shown in this figure, so here the disk is device, right? And this controller is the device controller, right? So it can be like uh, this controller can be, is it possible that it is a component of the device itself, or it is an external component and attached to the device and responsible for managing the device? So we have one disk controller per device, and each disk controller maintains local buffers and some special purpose registers. So basically what we are saying is that this disk controller has a local buffer here, and this USB controller also has internally there is a local buffer, and so on. Also same is true for, like, let's say, graphic adapter and so on, right? And then this disk controller, all of these controllers are piece of hardware, right? Remember, just like you have used the microcontroller in the 2230 course. So that microcontroller also has uh, different kind of special purpose registers. So these controllers also have special purpose register, and if you want to, like, interact with these controllers, then you need to know that what is the purpose of each register and what is meaning of writing one or zeros into different bit fields of those registers, right? So the job of the device controller is basically to move the data between the device and the local buffer. So this controller is responsible, let's say, only for transferring the data from the disk into the local buffer, or from local buffer into the disk. So this is like two-way transfer, right? So so the job of the disk controller is the data movement between its own local buffer and the device which it is controlling. On the other hand, device driver, it is a piece of software and it is running on the CPU. So definitely if it's a piece of software, so it must be executed on CPU, right? So, however, the important characteristic of a driver is that it understands the architecture of the device controller. So if you have a device driver for a disk running on the CPU here, let's say, then that device controller will know that, okay, what are different kind of registers in the disk controller, and what I need to write, and in what particular register I need to write to start an data transfer from a particular location address in the disk, right? The good thing about device drivers is that they provide a uniform interface to the device, which basically mean that uh, and keep in mind that device drivers are typically the component of the operating system. So providing a uniform interface means that uh, operating system doesn't need to worry about the vendor, the interface of the device which is provided by the vendor, or if the interface changes from one vendor to the other. As long as uh, our device driver knows the detail of the disk controller, and then it can manage the disk controller in a way where the operating system don't need to worry about the interface of the device. This is just like, for example, this is just like you write functions or procedures in a programming language, right? So as long as the input arguments and the return value is same, it doesn't matter for a user who is calling the function that how the internal details in that function are implemented, right? So for example, if I say I am writing a multiply function and I'm saying, okay, it takes two input A and B, and then it returns the product C. So that is enough for me. That information is enough for me to use that multiply function. Now, I don't care how internally within the body of the function the operation of multiplication is implemented, right? I don't care about it. So same thing is here. So device drivers, they provide you an interface. When I say view, it's mean they provide a interface to the uniform interface to the operating system for the devices that they are controlling. And their job is to move the data between a device local buffer and memory. Remember, the job of the device controller was to move the data from device, for example, disk here, into its local buffer. And then the job of the device driver, which is running on CPU, is to move the data from the local buffer of the device controller into the memory. or vice versa. Okay, any questions until this point? No? Okay, so here let's have a look at the timeline of how a device driver, which is component of the OS and definitely is running on the CPU, how it interacts with the device controller. So first thing is like, let's say our device driver, what does it do to start the interaction is that it loads an appropriate value in specific register of the device controller. Remember, we said that driver needs to know the internal details or features of the device controller. For example, what kind of registers it has and what is the meaning of each register, right? So it loads an appropriate value in specific register of device controller. For example, let's say it says read an input byte. The next thing that will happen in the process is that on the other side, the device controller, it will examine its register content. Actually, it will be examining its register content continuously, right? To find if there is the request placed. And once it sees that there is a request placed, then it performs some kind of action to handle the request. For example, if the request is to read an input byte, then as an action, it will start reading a byte size data into the local buffer, into its local buffer, which I have shown you, like tried to show you in the previous slide. So when operation is complete, for example, when it is done reading a byte-sized data into the local buffer, let's say here again, when it is done reading 1 byte of data from disk here into the local buffer, after that it goes to the step 4, where it informs the device driver. And once the device driver is notified, then it returns the received data from local buffer to the other part of OS. So it returns that received data. Like let's say if you want to copy that data into the memory, so then another part of the maybe OS or even the same device driver, the remaining component, the remaining code of the device driver will be responsible for copying the data from the local buffer of the device controller into the memory. But let's now try to be a little bit critical here and ask some questions. For example, when we say that at step 4, an operation is completed and device controller informs the device driver about the completion, the question is how it informs the device driver, through what mechanism, right? And the other question is that yes, on one side of the picture we have a device driver, on the other side we have device controller. So when the device driver is waiting for the device controller to complete the action, so should OS, or let's say the device driver, because device driver is component of OS, so should driver continuously check if job is finished or not? What should it do, right? uh, there are two possible answers to this question. One is that yes, it should continuously keep checking if the job is completed by the device driver or not. But if we do so, then it means that since device driver is running on the CPU and it is continuously checking whether the job is completed by the device driver or not, it's mean that CPU cannot be used for any other purpose, which mean that CPU will be kind of we are wasting the CPU because we are not doing any meaningful job other than just waiting for the device controller to finish this task or to complete its section, right? So we will be like wasting our resource, right? On the other hand, if we say that no, the operating system or the device driver should not continuously wait for the job to finish, then the question is how will CPU know that if the job is completed or not, if it is not continuously checking, right? If it is not continuously monitoring the device controller about the completion of the job, then how it will be informed that job is completed? So then the answer for that how is that we have a mechanism which are known as interrupt, right? And we will talk about them in next slides. If you have questions, you are free to stop me at any point. If you want, you can unmute yourself and directly ask the question. or as another option, you can send a text in the chat box. Okay, so let's first have a look at how interrupts are handled, right? So we said that the problem is, like we said, there are two options. Either your device driver can continuously monitor whether the device driver is done with the required action and or not. If if it continuously wait, then it's mean that we are wasting the CPU. On the other side, if we say that no, we will not wait, then the question is how will CPU know, or how the device driver will know that okay, the device controller is done with the required action, right? So we said that interrupt is the thing which enable us, which enables uh, CPU or the or the device driver running on the CPU to be informed when the device driver is done with its task. Right now, let's have a look at how interrupts are handled. Right. So let's say you have on one side you have CPU, and on the other side you have a device controller, or a IO controller, right? So input output, like mean you are getting input from any from the from the outside world, or you are giving the data, providing the data to the outside world, right? Any kind of IO device. So your disk is an IO device, your printer is an IO device, your screen or your monitor is an IO device, and so on and so forth, right? So so device driver, it first initiates an IO, just like in the previous example. It says okay, read a byte size data, and after initiating the IO or IO request, what does the CPU does it that it execute it CPU checks for interrupt between instructions. So what it happens is that here we are saying that now our CPU doesn't wait. It is not continuously monitoring the IO controller or the device controller to find whether the requested task has been completed or not. Instead, what it does is that it starts doing, or it starts executing some other program, or it's start doing some other computation, right? Definitely any other computation or any other program or piece of code consists of multiple instructions, right? So what it does is that after executing every instruction, it checks whether an interrupt is activated or not, right? If an interrupt is not activated, it continues with the next instruction. And once the next instruction is complete, it again checks whether an interrupt is activated or not. And who is going to activate the interrupt? Our device controller or IO controller, right? So on one side, we have CPU uh, executing instructions, and then between every two instruction, it checks whether the interrupt is activated or not. On the other side, whenever IO controller gets the request to initiate an IO, uh, input or output, so it will perform some specific action. For example, it will perform that input or output, and once it is done, it will like for example, when input is ready, or output data, the data which was sent by the CPU to be let's say displayed on the screen, and it is now displayed, which means basically that output is complete, or there is some kind of error in completing the required task. After after one of these three situations was happen, like your input is ready, your output is complete, or you were unable to complete the task, at that point, our IO controller, it sends an interrupt signal. So when it sends an interrupt signal, remember that our CPU is, yes, executing some other computation, doing some other computation, but also checking the interrupt signal in between every two instructions, right? So when our controller sends the interrupt at step 4, then CPU is able to detect that, okay, an interrupt signal was activated. And at that point, what it does is that it transfers control to the interrupt handler, right? Uh, Let me know if you are not able to understand, or if you have any confusion. Do you want me to explain it more using some figure, or it is pretty clear to everyone? Okay, I just want to let me go back. Uh, Let me go to the notepad and I don't know, maybe I can create okay. Yeah, so let me try to explain what we are trying to understand in this figure. So where is notepad? Yeah, yes. You just give me 1 minute. Okay. So suppose that you have CPU here, right? And then you had device. I'm just writing DD to indicate the device driver, and device driver is running on your CPU, right? And this device driver says, okay, uh, output some data, and it sends this request to your device controller. And then it takes some time for the device controller to output the data, right? So it is not like the job is completed in zero time. So let's say that this is the time period which is required to complete the task of outputting the data. Let's say to display the data on your screen, right? And let's say the data is not 1 byte or so it is not going to complete in zero time. In the meantime, uh, when the device controller is taking care of the action, requested action, what should our CPU do? As I said earlier, one thing is that one option is that we simply keep waiting for the device controller to complete the job. But then it means that in this time period here, we are simply wasting our CPU because it is not doing anything, right? So what we can do is that, okay, CPU, instead of waiting for the device controller to complete its job, it can run another program, right? Maybe which was waiting or which was waiting for its turn, right? So it can run another program. Let's say I'm naming it as program A. And let's say this program is consisted of multiple instructions, right? So here, then what happens is like, uh, after executing the first instruction, it checks is there an interrupt, and basically interrupt mean that has device controller sent me a signal that it has completed the requested task or not. So let's say there is no interrupt. So then it will go to the next instruction and execute this one. And after that, it will check again, is there an interrupt? Let's say this time there is an interrupt, right? So what will happen is that your CPU will stop executing, then will not execute the next instruction. And from this point onward, at this point, let's say here the interrupt arrived. So at this point onward, it will go to another piece of code, which is named as interrupt service routine. So it is actually basically a program, and it is also part of the operating system, which is responsible to take some action once the device controller is done with, if for example, in this case, with outputting the data, right? And then our operating system will run this ISR. And once this ISR is completed, our interrupt service routine is completed. After that, the control of execution will return back to the next instruction in the program A. And then it will continue in the same way, right? So this is what we were trying to understand. Now let me go back to the slides. So here, when CPU receives the interrupt, it transfers control through the interrupt handler, or ISR, which is also interrupt handler is also known as interrupt service routine. So actually, interrupt handler will invoke interrupt service routine, but for the time, at the end of the day, interrupt service routine will be invoked, right? So then interrupt handler, what it will do it that it will process the data. Which data? The data which is placed by the device controller in its local buffer. It retrieve the data let's say in the previous example, from disk and placed in the local buffer. So then interrupt handler, what it will do is that it will process that data from the local buffer, and then once it is done with processing that data, then it will return from the interrupt. Return from interrupt to what? To the same place, uh, uh, where to the same program which was interrupted. So for example, the CPU will resume processing of the interrupted task, just like I explained in OneNote. Yeah, I will take your question. Just give me 1 second. And after that, this cycle will continue in the same way. Let's say again, the program which we are running, or some other program is scheduled and it initiates a device driver request, and then again the request will be sent to the IO controller, the device controller, and so on, right? Okay, so looks like it makes sense. The CPU checks for interrupt signal after the controller is initiated. Once the action has been performed, an interrupt is sent from the controller, which pauses ongoing processes to so that the interrupt can be handled. Yeah, yeah, that's correct. Yeah, your understanding is correct. Yeah. Okay, so any questions or comments until this point? So please let me know. Okay. So this is how a CPU and how a device controller uh, interact with each other. But let's try to have a deeper look at this figure or this timeline, right? For example, how CPU knows an interrupt is raised, right? Uh, Earlier we were asking that how CPU knows that device control in the previous slide, we were asking that how CPU knows that device controller has completed its job. And we said that by mean of interrupts. Yeah, but how interrupt them, that interrupt signal itself is sensed by the CPU, right? Another question is that let's assume that there are different interrupt handlers for different type of interrupts. So here in this figure, this is a simplified figure, and we said IO controller. Let's say I simply instead of IO controller, I say disk controller, or and then there are other kind of controls like say USB controller. So uh, if there are different type of controllers or different types, if there are different type of devices, then definitely we will have different type of controllers. And if we have different type of controllers, then they need to be handled in different ways. We cannot handle an interrupt coming from the disk controller in the same way uh, as the interrupt coming from the USB, right? Because they both of them are designed for different functions, right? So it means that for the interrupt coming from the disk controller and for the interrupt coming from the, let's say, USB controller, we need to invoke different handlers, right? Or different interrupt service routine. So that then the question is that how CPU finds the right interrupt handler to transfer the control to. So for example, for the interrupt coming from the disk controller, we need to transfer the control to the interrupt handler 1. And for the interrupt coming from USB controller, let's say we need to transfer the control on arrival of the interrupt to interrupt handler 2, right? But then how does CPU know that how does CPU differentiate between these two different interrupts, right? So that it can invoke the correct interrupt handler. Another question is, okay, I think there is a question. Set different priorities for different interrupts. Uh, yeah, but even someone answered, I think someone tried to answer question number 2 by saying that set different priorities for different interrupts. Uh, Okay, I will not comment on the priority thing for the time being, but let's say even if you say that we can use the priorities to differentiate, but even then, how you know that which interrupt has higher priority as compared to the other available possible interrupts, right? So how still you need to differentiate, you need to identify, right, those interrupts, because only once you can identify, then you can assign them priorities. If you are not able to differentiate between two different interrupts, how can you assign them priorities? Whether priorities will work in this to will answer this particular question or not, it's a separate thing. But let's assume even if priorities is the right answer to the question too, still for that you first need to identify the interrupts so that you can differentiate between them. Uh, okay. Another question is like, uh, consider a situation where we are where OS invokes an interrupt handler, and then interrupt handler when while it is running, it overrides the register values which were produced by instructions that were executed by CPU before the interrupt handler is invoked. Uh, I know it sounds little confusing, but let me try to explain with an example. So let's say this is the task which was CPU executing here at this point. Uh, at this point, let's say CPU was executing this task, and it executed first instruction A is equal to 2, and then it checked, is there an interrupt signal? No. Then it went to next instruction, which says, let's say B is equal to 5. And after that, it checked, okay, is there an interrupt signal? Is fine. Oh, yeah, there is an interrupt signal received from the controller. So it then shifts the control to the ISR or interrupt handler, right? It starts executing the interrupt handler. And when an interrupt handler executes within the body of the ISR, it sets the register A, let's say, equal to 0. So let's say A and B are registers, which was like set to some values by task. But when ISR executes in its body, it also overrides the value of A and it sets it to 0. Now, when ISR is completed and the control is returned back to the task which was interrupted, right? So let's say the next statement, the next instruction and that task is C is equal to A plus B, right? So when we do now A plus B, we find 5. Why 5? Because B is equal to 5, but A is overwritten. So 5 plus 0 is 5. However, we were expecting that it should be 7, right? Because this is a separate program, right? And this program is expecting that the value of the C is 7. So it's mean that now our program is corrupted. The task which was the program or the task which was interrupted because of the signal coming from the device controller. Once the ISR is completed and the control is returned back to it, the computation results generated by that program or the task are not valid, right? So what should we do to handle this kind of situation? Another thing is that how CPU knows where to resume the interrupt. Here we are just like making things very simple. Here we are saying that okay, once the ISR is completed, the execution control returns back to the task which is interrupted. But how does the CPU know that C is equal to A plus B is the next instruction to execute once the ISR is completed? Because it was interrupted after B is equal to 5, right? But what mechanism is used to track that what next instruction need to be executed once ISR is completed, right? Okay, okay. Okay. Uh, Another question which we can ask is that what if multiple device controllers raise interrupts simultaneously? As I said, this figure is simplified, but in actual a real situation, you have multiple device controllers which are active at the same time, and it is possible that they can raise the interrupts. Device controllers can raise the interrupts simultaneously. If that happens, then how should we manage the situation, right? Uh, the CPU or the operating system, uh, actually operating system is running on the CPU. That's why I keep saying them interchangeably like CPU or OS. But the thing is that definitely OS is running on the CPU. So how should OS manage the situation? Like which one, let's say if three different interrupts are raised simultaneously, which one of them should be taken care of first, and which other two should wait? And on based of what criteria we select the we give the higher priority to the one interrupt to one of the interrupts and lower priority to the other interrupts, right? Uh, Also, let's say that a CPU is executing a task, a high priority task, and in the meantime, an interrupt happens or an interrupt arises from a device controller. So the task which the CPU is executing is critical and we cannot interrupt it. So if we cannot interrupt it, then what should happen with the interrupt raised by the device controller? Should we just ignore it, or should we just tell the device controller to raise the interrupt again after certain amount of time? What is our mechanism to handle this kind of situation, right? So here we have raised different questions, and okay, some of you have tried to answer. Uh, so uh, let's go through their answers one by one. Or if you have answers, uh, you can share with me. If not, then definitely I can. Anyway, I will explain them to you. So anyone who want to answer the first, how CPU knows an interrupt is raised? As I said, if I'm asking a question and you think it takes time to write in the chat box, you can directly unmute yourself and you can respond. Okay, so there is an input line, or there is an input signal uh, named as interrupt request line. So what does the CPU normally do is that after executing every instruction, it checks that input signal or input line. So to find if that interrupt request line is set high by any device controller or not. So which definitely means that on the other side of the signal, it is job of the device controller to drive it high when it is done with the required requested task, right? And after every instruction execution, the hardware will sense that signal. So if that signal is active, then OS will know, okay, an interrupt is activated and I need to stop doing whatever I'm doing, and I need to first handle this interrupt. Okay, so second question is like, if there are different interrupt handlers for different type of interrupts, then how can we like identify them? Just like we assign student IDs to this, we assign unique student ID to each student, right? So in the same way, what we can do is like we can assign IDs to the interrupts, unique IDs to interrupts coming from different device controllers. So like let's say if an interrupt is raised by the disk controller, so I can say, okay, your ID is one. So whenever you raise the interrupt request line, also set that ID to one, the ID line to one. And for to USB controller, we have assigned, let's say, the ID to two, ID2. So whenever now USB controller will interrupt, raise an interrupt, it will also send its ID. So in that way, the CPU will be, our OS will, hardware will sense the ID, and then based on reading of the ID, OS will be able to differentiate between different kind of ID, different kind of interrupts, and then handle them accordingly. We will talk about it in upcoming slides. Okay, so question 3, what if interrupt handler overrides register values produced by instruction executed by CPU? Just like explained as I explained it earlier in the example. So how can we handle that situation? ISR should push register values to stack. Yeah, yeah, that is correct. So remember in the like in the example we said like what if a ISR sets a equal to 0? So a is just like an a representation of the register, right? So then if ISR is going to overwrite any registers, so its first job is to store the older values of those registers in memory, or let's say the stack portion of the memory. Let's keep it simple. To store the old values of the registers in memory and then modify it as it needs to modify. And once it is done with its, once the body of the ISR is executed, before exiting from the ISR, those values are reloaded, are restored into the registers from memory, right? Okay. So on entering ISR, to be modified register must be saved in memory, and on exiting ISR must reload those saved registers from memory. Okay. And how CPU knows where to resume the interrupted task? Uh, Again, we need to keep track of things, right? So we just need to keep track of like where was uh, what was the location in the program which was interrupted, and what instruction was supposed to be executed next. So that information is tracked by a register named as program counter. And if you have taken the course on AVR microcontroller 2230, then I guess you guys know what is the job of the program counter. So it actually uh, holds the address of the next instruction to be executed, right? So when an ISR happens, so the first job, among other, just like I said, that you need to store the registers in the memory before modifying them. At the same time, the ISR also is responsible for storing the value of the PC or the program counter in memory. And then it starts executing the instructions in the body of the ISR. And to return to the point uh, of the program which was interrupted, so before returning from the ISR, that PC register is reloaded or restored from memory. Okay, and what if multiple device controller raise interrupts simultaneously? So then for that we use the priority. We, like as I said earlier, we assign IDs to different to interrupts coming from different device controllers. But not only that, we also assign them priorities. So which basically mean like if two interrupts are arriving at the same time, then we'll look at their priority level, and the one which has higher priority is taken care of first, and the other one needs to be wait or need to be raised again by the corresponding device controller. Okay, and what if an interrupt is raised when CPU is executing a task that should not be interrupted? Then the thing is like if you don't want the interrupt to happen when you are executing a critical task, so before starting the execution of the critical task, disable the interrupts before starting the task, and once you are done with that critical task, re-enable the interrupts and then y- upon the completion of the task. So which basically mean that once you re-enable, then you will be able to take care of the interrupts. So basically there are some interrupts, as you will see later. There are different categories of interrupts. Some of them are maskable, and when we say maskable, they can be disabled. You can enable and disable them. However, there are some other interrupts which are not maskable. So why? Because they are critical and they need to be taken care of at the time when they happen, right? So we'll talk about them later. Okay, any questions?
Hi. So I have a question.
Yeah, go ahead.
Yeah, so is there a register for the interrupt also?
Is there a register for?
For the interrupt. So I'm wondering like if there is multiple interrupt
Yeah,
and
yeah.
it will take care of it based on priority, right?
Yeah.
So how will you go back to those other interrupt that came in the same time? Is there a register for all those interrupt also?
Yeah, yeah. So actually, in your computing hardware, you normally have a component which is named as interrupt controller, which is responsible for reading the all the related information, for example, interrupt ID, and store it in the corresponding registers. And then your software, which is like your OS, is responsible for reading those registers and identify those IDs. So yes, you have to have those registers or latching places where you can store the interrupt IDs or all other related information.
All right,
Did I
thank
answer
you.
your question or not?
All right, thanks. Thank you.
Okay. Uh, okay. So we have 10 more minutes and we don't have quiz today, so I can make use of these 10 minutes. So let's have a look at a generic interrupt service routine, like how it works. Remember, we said that in the previous slide, we said that when an interrupt happens and the CPU detects it, the operating system, what it does it that whatever program or whatever application was running, it is then interrupted and the control is shifted to the interrupt service routine or interrupt handler. But how internally at a high level, in a pseudo level, an interrupt service routine looks like, right? So on the right side of this slide, you see a block diagram of memory, right? And in the memory, you have interrupt service routine for different devices. Like for example, interrupt service routine for memory controller, disk controller, network adapter, graphics adapter, and so on, right? So basically, what we are saying is that if an interrupt is raised by memory controller, we will we our target is to execute this program ISR memory controller. If a interrupt is raised by disk controller, then control base should be transferred to the this program ISR disk controller and so on, right? So how this happens, right? How we transfer the control to the appropriate ISR. So this is like a pseudocode of how an interrupt, a generic interrupt service routine looks like. So let's say you are waiting for an interrupt to happen, right? So what you do is that uh, you execute next instruction and then you look at while interrupt not detected. So if there is no interrupt request line is not activated, it's mean there is no interrupt. So you keep executing the next instruction, right? But once the interrupt is detected, then you transfer the control to this. Again, this is just a pseudocode to convey the idea how things work, right? So you run this function, run ISR, and which takes as an input the interrupt number. Remember, we said that if there are interrupts coming from different devices, we assign them the interrupt number, right? Then in the body of this function, what you have that you, again, this is just pseudocode. So you have a switch statement. So based on the interrupt number, you jump to the correct ISR. So let's say if interrupt number is 1, you go to the ISR of memory controller. If it is 2, you go to ISR of disk controller and so on, right? And if it is not taken care of in the code, then you simply say that this is an illegal or invalid interrupt number. So the good thing about this approach of handling different type of different type of interrupts is that you have only one routine which handles all the interrupts. So here you have only this one function which is then invoked and then it takes care of all different kind of interrupts like ISR for memory controller, disk controller, network, graphic adapter, and so on, right? However, the bad thing about this thing is, okay, maybe you guys can tell me what is the bad side or downside of this way of handling the interrupts. Is there anything bad about this approach? Any downside, any performance issue? Yeah, yeah, that's correct. That's correct.
Because you would need one for every single possible interrupt, which would build up over time, right? It's not as adaptable.
Say it again.
Or you would need a new case for every single possible interrupt. So you'd need to like either manually go in there or it wouldn't be adaptable if you had one that wasn't on the list.
Uh, uh, hmm, you will need, I mean, whenever you are integrating a new device, which is not already taken care of by your current OS code, then you have to write a new, you have to write an new piece of code to take care of the interrupts coming from that device. So uh, let's say we have uh, so yeah, I mean you need to modify, but even the alternative of this approach, they will also need to be modified if you want to integrate a new device and or introduce a new interrupt service routine, right? So the as some other students said, the problem with this approach is that it has ON runtime. So where N is like number of unique uh, interrupt IDs. So in the worst case, right? So let's say so you need to check all these cases like case one, two, three, four. Sometime maybe your interrupt number is let's say one. So you just check case one and you are done, right? You don't go to two, three, and four. But what if you have interrupt number four, then you need to check all the cases one, two, three, and then you have a hit at case four, right? But you need to go through all this if else. Actually, it is an if else, right? Equivalent of if else. So you need to go through all that if else branches. Uh, so it is slow as general routines checks all subroutines one by one. So just consider a case like where you have a hundred of different ISRs for to take care of different devices. So what if it is the last one in series of hundreds of checks, right? So it will take time. So the problem is that and why that is important, why we don't want our interrupt handling to be slow, why we want to be faster, because interrupts occur very frequently. It's not like they are rare. So for example, when you are pressing keys on a keyboard, so you are generating interrupts and they need to be handled efficiently. So if something is happening frequently, then you need to handle it efficiently. Let's stop here because otherwise I will not be able to complete the next slide. We have 2 minutes left. Uh, we will talk about how we can address this problem of generic interrupt service routine handling in the next slide, in the next lecture, and we will continue from there. Any questions at this point? No? Okay, if no questions, then let's stop here. And remember, you will have first quiz on Thursday. Okay. Okay, then have a good day.